So today's going to be about, I'm going to talk about analysis of brain imaging data, and you got to work, basically. So all of you should pull out their laptop. And so first thing that you want to do is do Twitter. So you just Twitter Andrea Giovannucci, my name, OK? If you do that, you'll see my tweet, OK? And there is a link to a collaboratory file. I'm going to show you. MATLAB open. It's going to the wrong place. But basically, there it is. OK, you should see this link. If you click, you'll be brought to 4 demonstration files, OK? So what's cool about this is called Google Collaboratory. And basically, they offer you virtual machines with GPUs. And you can start trying doing analysis with a reasonable computational power, OK? So normally, if you go there, you will click on one of them. And what you can do is open with. And you should do Google Collaboratory, OK? Something like this will pop up, OK? If everything goes well, you should be able to see something like this popping on your computer, OK? So Changjia here can help you if you have issues with that. You just ask him. We're going to start with one. It's called Demo Pipeline. I want to have everyone on board whenever you are ready. So you don't have a computer. I mean, everybody should try. I really spent a lot of time for getting this perfect. OK, so what happens? You open this, and the only thing you want to do at the beginning, you go to Edit, Notable Settings, and you want to add an hardware acceleration, GPU. And see it there. OK?
That option is grayed out.
Is it? I mean, it's not dramatically necessary. We can fix it, but it shouldn't be grayed out. You guys have problem? It's grayed out for you? You should be logged in, with your Google account, of course.
Yeah, I am. Yeah.
Do you guys have problems, or do you can set it to GPU? Did you manage to set to GPU?
Can you just show that step one more time? Yeah. Sorry, I was a little behind.
Yeah, can you?
Going here? From here or from the tweet? Everybody got the Twitter?
Yeah.
Yes.
Good. So you go here and say Open with Google Collaboratory.
Okay.
You select Demo Pipeline as a file.
You should copy to your own.
You should copy to exactly. That's a good point. Probably you cannot. You go want to do here as save as a copy in Drive.
Yeah, okay.
Maybe that's why it doesn't work.
Yep, that fixed it.
Oh, save as copy.
I just set it to read mode so that other people can only save a copy.
This is only read mode, actually. That's why probably it's not able to run on GPU. So yeah, of course, this is set in such a way that you cannot change my file. So you have to have a copy yourself of it, OK? Then you go and as I mentioned before, you try again to go to Notable Setting and add a GPU here. That means now you have a machine with a GPU.
I missed your, how do you get to the notebook setting?
Oh, here.
That was super fast.
Edit,
Edit.
Notebook Settings. I'm going to wait for all of you, so don't worry. We're going to get this. Once this is set, the rest should be easy. Right? Is it working? Cool. So, so again, yes, you have to do save a copy in Drive. and give it the name you want.
You
did say copy that.
can see in my drive storage.
Right? So basically, this is a remote computer now, okay?
Which GPU now?
I don't know. But you can, see, it's Google, it's Google, it's Google, it's Google.
You pay for it?
No, you don't pay for it. So if you use just one GPU and one, so basically how does this work? They will give you time on this machine and a GPU, but the deal is that when you disconnect, you have to reinstall everything from the scratch, okay? So it's not a permanent machine. It's just created for you temporarily, okay? And that's why we install basically everything from the scratch, but don't worry, it just takes 1 minute. Okay. So what I suggest that you do, you go to runtime and press run all. So we bring ourselves forward. Okay, and as I explained to you, so don't worry, I didn't put anything malicious, you can run it. Okay, and if everything goes well, this should start installing Cayman for you on that machine. Okay, so it's gonna go to the repository, okay, where we keep the software on GitHub. It's gonna install the required files that you need. It's gonna install Cayman, and then it's setting up Cayman so that you have your demonstrations in place. Okay.
Dang, that's cool.
And then all of this will go as I explained to you. What I have to talk about today. But if you have troubles, please stop me. I think what's the most important thing that should happen today, you go home and being able to analyze your data. Okay? The only thing you want to be able to do is move it to a drive. You can mount your Google Drive and run it from there. Okay. As the software works for us, we're going to tell you a little bit about the theory behind it. Okay, this is the structure of the talk. I hope I will be able to cover all of these topics. First is going to be motion correction and memory mapping. Something was already mentioned by Simon. Then I switch to calcium imaging analysis. We will look at multiphoton. And then I'm going to look a little bit into single photon business. And that could be voltage imaging and CNMFE. That is basically analysis of endoscopic data, miniscopes. Okay, don't need to tell much about calcium imaging to this crowd, of course, just to let you know that this is revolutionary because we can target the cells that we want, we can image the portion of the neurons that we are interested in, we can do this across days in living animals. And, as we saw last time, we also are able to do it in animals that are freely moving. This is made possible by, of course, the two-photon nonlinearity. The nonlinearity in absorption of photon is two-photon, and then advances in microscopy. Once you get one of these neurons, you identify them, then you have the problem of basically extracting the activity from it. So extracting these fluorescence trace, that's one problem. And second, once you have the fluorescence trace to extract spikes or a possible.
Is this cerebellum data from Sam's lab?
Yes, I took that data. Yeah.
This is beautiful. Is that GCAM6 or what's the?
GCAM6, yeah.
Mainly complex spikes per se, or are you picking up some simple spike activity?
No, simple spike.
It's all complex?
Just complex. These are the dendrites. Even if there were simple spikes, you wouldn't pick them up from the dendrites.
So this is sped up a lot then?
It's sped up. It's sped up, yes. Thanks. It's GCAM that made the miracle. This is the hippocampus. This is just to explain it. He's very familiar with that, but you might not. These are just dendrites. So if you want, you can just see a lot of portions of the dendrites of the neuron without not even seeing the soma. And this is the hippocampus. Okay, this data is from the Tank Lab. Okay, and then we have single photon imaging. Of course, opens the path to fantastic opportunities, but comes with a big baggage of problems. Okay, so here we have example of endoscopic data. You already see that the difference between this and what we just saw in the other movie. and then you have calcium imaging. Sorry, I swapped the labels here. This is calcium and this is voltage. So basically, at voltage imaging, you see the signal-to-noise ratio now is decreasing dramatically. And not only that, these are collected at 30 hertz, and these are collected at 400 hertz. So we're going to, in the second part, looking at these things. There is another distinction in the analysis that we want to do. One is batch analysis. That means I have all the movie, and I just want to analyze it. Okay? I get all of it. I will get out my neurons and my traces. And the more interesting and relevant is, to me, for modern experimental techniques, is online. That means I have so much information about my data so far, and now frame by frame, I want to approximate the activity of the brain and eventually find the new neurons if they appear in my field of view. So this is a general framework that, a pipeline, as Simon put it before, that in most cases, both calcium imaging, voltage imaging, one photon, two photon imaging, and online or batch, they have to go through. And it is motion correction, okay, correcting for motion, initialization, that means find a rough approximation of where the neurons are, then perform some denoising or source separation. That means the traces as we took them as an average of the pixel, that's not enough. Look at this case, for instance, right? If you have these three neurons and you take the average, there will be a lot of leakage of one neuron over the other one. So you want to find methods that are able to separate these neurons into three different and also separate their traces. Okay? In the case of voltage imaging, we might want to clean up the data. The data will go up and down because of subthreshold oscillations, because of background signal. So also all that stuff needs to be cleaned up. Okay? And the final phase is extracting spikes or an approximation of them, both in voltage imaging, where it's actually easier, because a spike is just a spike, whereas in the case of calcium imaging, the signal is, the relationship between the spikes and the fluorescence trace is very nonlinear. Okay? You might even have spikes and not having any blip in your trace. Then you have two spikes, and then you have a big blip in your trace. So there is no linearity in that. So that's what Simon also before mentioned, that we need to work a little bit more on that. That's not a solved problem at all.
So are you able to separate out the sub-threshold voltage?
We didn't try. Actually, that's part of the future work. Yeah, that's something that needs to be done. So something can be picked up, of course, but we didn't systematically look at it. But there is signal. You'll see it. You can clearly see subthreshold oscillation. You can see all the neurons going up and down. Later in the demo. Okay, so let's start with motion correction and mapping. The way it will go, I'm going to explain you the concept, then we go into the demo and look at what happened into the demonstrations and all the parameters that you need to set. Okay, why do we need to motion correct? Well, basically, most of the algorithms that we want to use to analyze calcium imaging data will assume that the same pixel will always correspond to the same structure. Okay? So anatomy and pixels should be mapped one-to-one. If the brain moves under the microscope for some reason, the brain is mushy, it's not hard, so it will move. And as you might see here, and it was mentioned previously, often it will move in a non-rigid way. Okay? So this means that if you try to correct just moving with rigid translation, your field of view, to try to overlap, that's not going to be enough. And at that point, what you need to do is to basically find new ways of correcting your field of view in which you deform your frame in order to map to a given template. Okay? So we call the first one rigid motion correction, and the second one we call piecewise rigid. Okay? The trick that we use is basically, I think it's the first thing that might come into mind to someone that wants to try to solve the problem. We motion correct different portions of the field of view, okay? And each of them will have different shift. And then we basically interpolate the shifts between these different squares to reconstruct a smooth, let's call it shift field. Okay, so you correct this, you correct this, you correct this. Each of them will have its own shifts. for instance, if you look at these movies, these guys will move a lot, and the guys on the left will move very little. Okay?
You want to comment on why you use that approach rather than, full field or sift or something like that?
So basically, this state, as I told you, what we did is like, what is the simplest thing you can do? We had in mind a lot to be fast. So this needs to be fast. So that's why we motivated this one, because this is easy in some sense to parallelize and do stuff like that. The other methods that we tried so far, where we have a paper in Normcore, they were not working very well. But I want to say now, and because I will get a lot of questions, the devil is in the details. So it means that you might get many algorithms, and what happens is that if you find the right set of parameters, they will work for you. So we compared 3 or 4 algorithms in the paper, and we found that, of course, our was working better, but this also could be because. So what happens is that in reality of life, a lot of people are using these algorithms, so this makes us feel that probably it's a good choice.
Yeah, no, I can say the speed of rigid, and that's also probably going to capture most of the, there's probably relatively low degree of deformations, at least in the data that I'm seeing right here. But I'm guessing this also helps, is helped by the fact that the scene is raster scanned from the top to the bottom. And so doing it block-wise, doing it at least segment-wise, if not block-wise, probably works better than doing the whole field.
Yeah, absolutely. So like, precisely, another approach, was trying to basically correct up in slices, like there was just before us. And you know why that was happening? Because they were scanning at 15 hertz.
Yeah.
So what happens? You scan at 15 hertz is the most likely deformation that you get is from a slow scanning. And as you, again, to follow up on your point, what's good about this method is that what we can do is check first what's the rigid shift, right? So the rigid shift will tell you that everyone is more or less going one direction. So what you can do, you start putting constraints on each of these blocks that they cannot deviate much from the rigid deviation, right? Because if the rigid deviation goes in this direction, it's very unlikely that this square will go in the opposite one.
Okay.
So basically, you have also, you can use information from both from the rigid translation plus from each of them, and plus from the fact that if they are neighbors, they will not be able to shift a lot from among them. So this is the, it was a bit of a long answer. I don't know if it make the point.
I appreciate the detail.
Thanks. Okay, so let's go back into what kind of parameters you might want to set. And I'm going to try to focus on the one that are really important, and maybe slide on the one that you can, at least in the first order approximation, not set. So here we have the frame rate, very easy. Then you want to set your decay time. This mostly depends on your indicator. This is the tau off of your indicator. If you have GCAM6S, for instance, this should be around 1.2 seconds. For GCAM6F that we are using is 0.4. The XY is your spatial resolution in X and Y in microns. Okay? So basically, here you can then express the max shift that you allow. So you'll have different cases. You want to constrain your algorithm to do the right shifts, right? If you have a very stable brain, which I hope you have, then you will have a very small number here, maybe only 6 micron shifts at top. But if you have a brain that moves a lot, for instance, you are zooming a lot into your samples, then your swings can become larger, and then you can set these by the microns, maximum microns of shifts that you allow for your fields of view. And secondly, you want to do the patch motion. Patch motion means how big should these patches be, and this is probably a difficult parameter to set. If you have a very dense field of view, then you can probably, equally illuminated, that probably you are okay with a small number. But if you begin having a lot of areas with few neurons, then you want to grow these ones. Why? Why? Because if you start having many of them that behave erratically, then this will create some weird deformation in your field of view. Then here is basically is a flag that tells you if you want to have piecewise rigid or rigid, as I explained you before, motion corrections. Piecewise rigid is slower, still okay, but rigid is really, really fast. So if you, my suggestion is first thing you try rigid. If it doesn't work, you go to piecewise rigid. Maximum shifts. This is just a computation from your, basically for setting up your resolution. So forget about that. Overlaps. This is maybe the one that you might want to change if something goes wrong. If you see that these guys are behaving a little bit erratically, that means that you have deformation of your field of view after motion correction, then you want to change this, increase it. And max deviation rigid is the parameter that tells you how far, basically, these patches can go with respect to the rigid shift. So if the rigid shift goes this way is 5, okay, this cannot go 1 or 2 in this direction. So you need to follow. In general, you just need to set this one up there.
Wait, so you do the global rigid shift first, and then on top of it the piecewise rigid?
We do the piecewise, we do everything at the same time, but we use the information from the rigid to basically discard possible shifts that are unrealistic. But no, you do everything in a single step. But you can decide to turn it off if you want something fast in terms of answer. So today that we don't, so this algorithm comes highly parallelized, as I can, I'll tell you later. Basically, the output of this is a memory map file. So what we try to do is to save directly in a format that is easily readable from you. That means if you have a 200 gigabyte movie, you don't want to load that in memory. So this will save you in a format in which you can randomly access from your hard drive any frame. Okay? What's important is this is very efficient when you read each frame. If you read frame 200, frame 2000, frame 10,000, this is very efficient. If you try to read pixel 1 across time, this will be dramatically slow, hours slow, okay? Because this is really organizing your hard drive in such a way that you can read frame by frame. And how does that work? Just to give you a quick scheme, there is a big movie. So we have several processes, several parallel processes in your computer. You got different chunks of them to your machine. Each of them will be independently motion corrected. Okay? Each of them will create a template. The template is very important. That means what's your reference image you are aligning everyone to. Each of them will create a template. Then we'll create a template of templates that we call master template, and then iterate. Okay? So basically, you are refining more and more the ideal, okay, field of view that you have. Okay? That's important. Why? Because you are using a cross-correlation measure. So what you want to have is the cleanest possible representation of your field of view to align all of the frames to it. Any questions about that? Okay. Since what we have was able to read very efficiently in only frame by frame, we also create another file that actually can be read efficiently pixel by pixel. Okay? This is an operation that Kaiman can do, and I will show you later why also this is important. Now let's go 1 second to the demonstration, okay, and see if this worked, first of all, for you and for me. So it seemed to have worked for me, luckily. So basically at the beginning you are just set this blah, 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 blah. What you want to start, where you want to start is here, okay? This tells you, okay, there is a demo file that is called Sue Ann, a friend of mine. She took this data. This download the file for you on your computer. First thing you can do, we figure out how to play these movies on this website. So you can look at the data. Do you guys all have this? You can see it? You press play and you can have a look at your data. In order to make it nicer, we downsampled it, by a factor of 5, and in time. But this, you can even look the original movies if you want. Okay. Then here, what we did is set some parameters. Okay. I explained to you the parameters before relative to motion correction. We decided not to do motion correction, so piecewise rigid parameters is set to false. We create a dictionary of parameters, and then we start a cluster. So that's the neat thing about this. Will have zero effect on this machine because there's only one processor. Because Google doesn't give you 10 processors, that would be too much. But it gives you one processor. But if you do it on your machine and you have 24 cores, this will create 24 small workers, and each of them will work together to basically speed up your computation. So we create this little cluster on your machine, and then we start motion correcting. Okay? And the syntax is very simple. We create a motion correction object. We pass the name of the files that we want to motion correct. We pass the cluster and the options that we set up before. That's it. Okay? There's some, operations that you want to do to remove the borders, because the borders might, as you motion correct, the border disappear, of course. So you want to compensate for that. And then you call your motion correct function, and this will motion correct. And you can have a look at the results of the motion correction. Okay? So you should have this done on your computer. And what do you notice here? Is there anything that popped to your eyes looking at this motion corrected movie?
Stretching.
Stretching, exactly. So I have an exercise for you, and it would be try to run this now with piecewise rigid motion correction. There is only one line that you need to change. It's gonna take a long time, of course, now because you have only one process, okay? So don't run it, just show it to me. So I'm gonna show it to you, so don't run it because otherwise it's gonna take ages.
Yeah, this is this.
So basically, the only thing you want to change is this, and you're set, okay? So don't try it now, please, otherwise you will not be able to see the rest of the demo. Too late? You can open another one, it's free, so. Okay, so we looked at that, and then, as I mentioned you before, we create this other memory map file. So what's super cool about this now, you have the bad thing, you're going to have 3 copies of your movies on your hard drive. It's only temporarily, though. But the cool thing is that now you can look at this movie in any direction that you want. You want to see frame 10,000 to 20,000. Tap. You load it very quickly. You just take what you're interested in. You want to see pixel 1 and pixel 3000. You can do that, too. OK? Cool. Let's go back. And now we are continuing with the analysis. I suspect I have 2 of these guys open, right? Okay. I gave you that. Okay. As I mentioned to you before, there are 2 types of analysis. One is you get the whole movie in memory, and one you just analyze frame by frame. So we're going to start with all the movie in memory. A little bit of math, very little. Basically, the framework that we are using and we found to be very effective is something that my colleague Eftikios Pneumatikakis thought about a few years ago. It's called CNMF, that stands for Constrained Non-Negative Matrix Factorization. The idea is reasonably simple. Basically, you take a movie and you decompose it into the sum of different components, and each of these components corresponds either to neurons, okay, we call this matrix A, and this is represented by a spatial and a temporal component, plus neuropil or background. The neuropil and background is also basically defined by 2 components, the spatial distribution of fluorescence and the temporal distribution of fluorescence. Okay? So the idea of this NMF is basically by summing all of these guys, you are able to approximate this. That in mathematical terms, it means that you are solving this optimization problem. Okay? This is the movie, these are the neurons, this is the background, and you are minimizing the norm 2 of them. With the constraints that A is sparse. Sparse means that only few pixels will be occupied by neurons. This seems a natural constraint. And non-negativity. That means that you don't want to have negative signals here. That is also very reasonable, because this is spatial footprint, positive, and these are calcium traces, also positive in general. Okay, just to give you more of an intuition about that, imagine that this is the movie we are looking at. The spatial component is one column of this matrix, and the temporal components is one row on of this matrix. So when you basically do the outer product of these two, you are able to reconstruct the contribution of only one neuron to your movie. Okay, that's the trick. Basically, this decomposes in the contribution of each neurons, and each neuron is defined as a group of pixels that will go up or go up or down together in fluorescence at the same time. For the background, we have something very similar. So the background will look something like that. And you can see here that at some point it seems that everything becomes brighter, everything becomes dimmer. And that's a very bad signal to have mixed to your neuronal signal. You don't want to have it. Okay, and this is a very nice illustration of how this works. I looked a lot of these movies because I think they give you a better idea of what's happening over there. This is the original raw movie. This is the movie that you reconstruct using your inferred neurons and background. Okay. And here you have, more interestingly, your components only the movie that is reconstructed only using the neurons. Okay. Here we find the residual. What is the residual? The residual is that if I take from my raw movie whatever I reconstructed, if I subtract from this, what is left? Okay? And this gives me an information about how well I did my job of finding neurons. If I see a big structure appearing here, that means that something failed in the algorithm. So what you get is an output, just to summarize, this matrix A, that are the neuronal components, and the spatial and the temporal components. So basically the calcium traces, or a denoised version of the calcium traces. Okay, a little bit more into the detail. So after motion correction and memory mapping that we just saw, we start exploiting parallelization in the direction of the patches. Okay? If you take your field of view, you can divide it in several patches, okay, and process each patch separately. This gives you an initialization of an algorithm. If you remember, we try to find approximately where the neurons are. Sorry. This is the representation of it. Okay? So if we try to solve the problem of finding neuron in this little patch, or if you try to solve the problem of finding neuron in this big patch, it's basically the same problem, if you take into account what happens to the borders. So we solve many of these little problems all around, all in parallel. Okay, we take chunks of the movies, tensors, slice tensor of this big movie. We send them to different CPUs. Okay, we find the neuron there, and then we process the borders on the side afterwards. Okay, in this way you can parallelize arbitrarily. Well, not arbitrarily, but you can parallelize significantly the computations that are performed on this big field of view. So, and now we go back. Why do we need to be able to read efficiently this movie in the direction of pixels? Remember, because when you try to extract these big cubes, you don't want to load in memory the whole thing. You just want this little slice. So what we created before in a memory map format allows us now to access this directly and without having to load in memory anything, basically. The parameters that you want to set are these RF. Basically, RF is half of this side. So an RF of 15 pixels means that you have 30 pixels of patch size. the stride is basically the overlap between the patches. And k equal 4 is very important, is the number of neurons that you expect to find this little patch. Okay? So when you initialize your algorithm, you want to look at a little patch that is maybe 30 by 30, say, okay, approximately how many neurons can I find here? And you put this into k. Okay, this is basically it. We use a cluster, as I told you before. These are other parameters that I'm going to explain one by one, and then we're going to look at the demo. P equal 1. This the order of autoregressive system. You might have noticed that the traces, the calcium trace, look very denoised, look very smooth, and there is no noise around them. Because we use a dynamical model to basically extract, to denoise these cells. And P equal 1 or P equal 2 tell us how precise is the dynamical model. Okay? And as a general rule, what you want to do is to use P equal 1 when you have a signal that is fast with respect to your sample rate, and P equal 2 when your signal is slow with respect to sampling rate. And more like, even more in detail, if you look at your calcium transient, if the calcium transient look like this, then use P equal 1. If your calcium transient look like this, then you use P equal 2. Because P equal 1 will just capture this segment, and P equal 2 will fit both this and this part of the curve. Is it clear? It's basically as you want to just capture the decay time that is normally slow, or you also want to be able to capture the rise time of your transient. GNB, we talked about the background. The background is your neuropil, okay? So how precise do you want to be in capturing the neuropil? You might just have a very uniform neuropil that everybody varies at the same time, so you just need a GNB equal 1. That's the number of backgrounds. But if you have a complex background, maybe you have one part of the field of view that goes up, the other part of the field of view that goes down, then you want to have multiple of these. You don't want to exaggerate, because if you take too many of these, they will begin sucking up the activity of your neuron. We'll see exactly what I mean when we're talking about single photon data, where the background is really higher order, and it's even difficult to capture with this model. Merge threshold is I mentioned that we need to look at the neurons basically after we compute like all the patches, what happens on the borders. Okay, on the borders often you will have to merge neurons. Okay, so what happens is you set a threshold to a posteriori merge neurons that are highly correlated in activity. So imagine that you have two neurons. The algorithm, for some, mysterious reason, will pick up two neurons that look like this. Okay, and their traces, they look basically the same. Okay, what do you want to do? You want to say, no, here there is just one neuron. Okay, it's not. So this merge threshold is the correlation coefficient between these two traces. So, for instance, if you're doing photomodulation, okay, and you create a lot of synchronous neurons, what you want to do, you want to try to increase this threshold, right? Imagine that you photomodulate a lot of neurons in the center of the field of view. They will become very synchronous because you are making them synchronous, and then you want to raise the threshold to merge them. Otherwise, they will all clump together. Yeah?
Will it only merge pixels that share the same XY or similar XY coordinates, or could it accidentally?
No. They must overlap at least by 1 pixel. Yeah. Otherwise, yeah. That's a very good question. If you have dendrites, you might have cases in which you want to, merge even things that don't overlap. It's an open problem. But no, in this case, you consider that basically at least 1 pixel overlaps. Okay, then we go to this parameter that I normally set very manually. this is half of the size of your neuron. So if your neuron is 9 pixels, 8 pixels, you will use 4, half of it. Okay? So what I do, I look at my image, I zoom in, and I check, okay, more or less how big are my neurons. I divide this number by 2, and I sum 1, and this is what I use. Okay? You should be okay without knowing what happens in these ones. Okay. So let's go back to the demo pipeline. I cannot. Okay, there it is. So we were here, we stopped the server, and we have other parameters that we set above and I didn't talk about. No, they're actually down there. See, here are the parameters that we chatted about. Okay. The only thing you want to change then for your data set, you go there and you change, you start playing with these values. That's what I do. You know, you must have a little bit of criteria. This is not the black box. That's why I give this lecture. But basically now you can start playing around until you don't find something that is satisfactory for your data set. And once you do this is very simple. These are the 2 lines that will launch Cayman. Okay, the first part of Cayman that basically run all of these patches in parallel and then merge together, put them together, everything in a single field of view. And you can check the result down here, okay, of what we did. Of course, what you see here is that we are exaggerating. There are far too many components where there is less neurons that are active than what we are looking for. This is done on purpose. Okay? We exaggerate the number of components that we want to find, and afterwards we clean up, we filter, and we just use the one that we want to keep. And that's the second part of our routine, basically, is to refine this result. Oh, I managed. I didn't manage. Is there any reason why? All right. Cool. So how does this work? Basically, we started with, we were working on different patches. There was this problem at the borders. But now that we have everything, we can still parallelize, okay, components by components, but now working on the full field of view, just using the components that we found so far. Okay? So we start refining the solution, okay, using this seed that we created, and then we are going to filter for quality. If you are unhappy, you can do this several times until you don't converge to your ideal solution. Okay? Then we can compute delta f over f or track neurons across days. I will not talk about track neurons across days, but it's everything in the paper, so very easy to check. Okay. When we refine solution, what do we look at? We look at basically 3 metrics. There are 3 metrics. One, of course, will be the signal-to-noise ratio. Okay? We have a way of measuring how big are the calcium transients with respect to our noise, and this is called SNR. And then we have a spatial metric that fundamentally compares the spatial component that we find with the average of the frames in which the neuron was active. So let's imagine that you can find all the frames in which this neuron was active and nobody around him was. You average them. The neuron will pop out, right? Because this neuron was active and everybody around was not. Then we compare with the mask that was found by the algorithm, and if the cross-correlation is high, then we accept the component. This is called Erval threshold. And finally, we have a convolutional neural network that has been trained basically to recognize what looks like a good neuron from what looks like crap. Example. This is the training set, okay? This, everyone can agree that these are neurons, right? They look like neurons. And then when we look at these ones, there are doubts. This one definitely has signal, but probably it's just an axon or a dendrite. So we train this network, a very, very small network, to decide, okay, for us, looking at a component, if it's a good one or a bad one. And this is a third threshold that is called CNN underscore threshold, and CNN lowest. We have two ways of using these thresholds. One is just accepting neurons that are above a given threshold. Like for instance, this means that you will accept everything that is above this threshold, but also everything that will be above this threshold, and also everything that will be above this threshold. But there is another modality that works very nicely. You reject everything that is below this threshold, no matter what the other values are. Okay? So we have either an OR of conditions or a single condition that overrides everyone. So for instance, let's see if you understood. This tells you how likely is to have a neuron. If I raise this number to 0.5, what will happen?
You reject more, right?
You reject more, and you reject what? Approximately, if you have to have an idea. Like for instance,
I don't know what that's just
among these one, do you see one that is most likely to be rejected?
the top right.
Top right. It's good. See, it doesn't look like a neuron a lot. So basically this is the neuronness of there. And if you use it up and down, this is a very selective criteria. Okay, it works really nicely. This is an example of what happened before applying the filters and after. Okay, this will not do 100% of your job, but it's going to do the 90% of your job. That I think is reasonable. Yes, do you want to do an exercise? Now let's go back to the I don't know what happens. I'm baffled. Okay, that's it. No, see, that's bad. That means I have to recompute everything. I spent too much time talking. But you know, the results is already there, so you can see it. So basically, this is what algorithm did for us, right? Okay. So this is the results of the filtering. The filtering is set here. You can set your variable here, not now because it's disconnected. See, I told you that Google randomly can disconnect your machine. In this case, it did it. Basically, everything is already computed and you can use, evaluate the components, and then you have now all of them separated thanks to this value, based on this value. You also have a way to basically exploring these components. This will show you basically the trace, the fluorescence trace, and the shape, okay, of the components that you selected, okay, and then down here the shape of the components that you rejected. Some of them are good, but they don't look like neuron. They might be other type of processes, right? For instance, this one. Let's see, there was one. Yeah, that looks really great, but maybe not very neurony. Why? Because maybe there was a long process, and you know, it was filtered out by the convolutional network. So your exercise that you will not, I don't know if it got disconnected or not to you. It got disconnected from me. If it's not disconnected, you can try to play with the parameters. For instance, if you now put this guy to 0, okay, and mean SNR to 5, what you will see is that you will select all the neurons with big transients. So you can play with what you are interested in at the end of the day. So we display the final results, and we can also have a look at the movie that has been generated. As I told you before, I like looking at the movie of the neurons afterwards. So you can play it and see what is the noise movie looking like, and it looks something like that. Okay? You can do the same then playing plotting the residual or plotting just the background if you want to have information about how your movie was decomposed. Do you have any question?
Is there any way you can manually accept or reject?
Yeah, not through this interface, but yes, if you... So basically, this is for demo purposes. Now, if you get serious, either you buy a lot of stuff on the cloud, you can, maybe Greg can buy it, or you can install it on your computer, and then you have a web interface, sorry, a GUI that basically allows you to select these neurons and reject other neurons. So you can definitely do that.
Does this system also works for the set of neurons that kind of like deform or like rotates?
So this system can work without the convolutional network, and in this case, it should work. So you can expect a lesser performance and more manual work on your end, but everything will work with any shape of neurons except dendrites. Dendrites is more problematic, but if they are roundish, it will work. The question is that you have to turn off the convolutional network or retrain the convolutional network adding your data, so that the convolutional network now knows that there is something else that should be considered neurons. Depend how badly they look also, you know. Is there any question thing that you didn't understand? Yeah.
How you have a feeling for how careful you need to be looking at a control group versus an experimental in the way you select parameters? So in other words,
yeah.
Are you doing a different kind of selection for one versus the other?
No, that's a very good point. So what we did is the following. We took 3 manual annotators, and we had them, you know, select manually, not using Kaiman, just selecting manually, and see what was the performance of themselves versus a consensus ground truth. Okay, how different were among them. And then we took this consensus, we trained the network, and we saw how the network was doing in some validation tests. Humans do better. They are more consistent. I can show this data if you want, but they are not super consistent. They, you know, there is a measure is called F1 score that combines basically precision recall, and humans are in the 85 to 95% range. That means that they can be very, very different labeling when used manually. Kaiman is around 85, so it's a bit lower, but reproducible. So everyone that uses Kaiman will do the same. That's the same. The second part is about extracting signal from neurons in real time. Okay, why would you want to do so? So first motivation is, of course, controlling neuroprosthetics limbs. Whatever you want to do to control some external artifact will need to to be linked to the activity of the neurons as fast as possible in real time. Secondly, if you're doing experiments with your mice, you might want to be able to modulate the environment. So for instance, the stimuli that you are delivering to your animals based on the current neuronal configuration. And finally, and most interesting, if you want to do all optical experiments, in which you can infer in real time the activity, the state of the network, and modulate it by using optogenetics, as for instance, the methods developed by Nico. Okay, we saw the requirements for calcium imaging before in the batch case, and there was motion correction, we recall. There was source separation, you know, that you don't want to have the activity of one neuron leaking into the other one, or the background. But new requirements, new constraints stems from this type of imaging modality. So one is that new neurons might appear. You are imaging in the hippocampus, and there might be neurons that they turn on only once every 4 or 5 hours, or maybe days. Okay? So if a new neuron appears, you want to capture it. And another important thing is that if you're thinking about long-term imaging, is that neurons might slightly change shape. Simon showed before that neurons can actually morph a little bit from one day to the other one. And the algorithm should capture that type of change. Plus, we will see, when you find a new neuron, you might find it because it does one spike. Okay? But you want to be able to accumulate more evidence and denoise better the neuron if more spikes appear. So if more spikes appear, you want to be able to refine the shape, or in general, the spatial footprint of the neuron. Now, there's no existing methods to solve online except this one, And the data rates at which we are working, they can be very high. So we go from 30 megabyte per second in a usual, basically in a standard setup to 110 megabyte per second when you do light sheet imaging. Okay, so the analysis pipeline is basically contain the same section as before. We initialize and in batch using the algorithm that I defined before. So we take a few frames, maybe 1,500 frames. We find some neurons, and then we from there we start and we iteratively at each frame correct for motion. We estimate the spike with the noise, and we extract the spikes. We detect new neurons, and we update the shapes. All of this is described in these papers if you are interested in more detail. And then the things repeats in this fashion. So I'm going to take out of the way spike extraction. OASIS is the algorithm that was mentioned before by Simon, is used for basically approximating spikes. These are not spikes. I want to stress this out. It's just, let's say, more precise representation in time of the activity that we extract from calcium data. But it's only an approximation of the spikes. So in real time, this is how the algorithm works. It's based on the work presented by Johannes Friedrich, a colleague, in an IPS paper. So if you are interested about this, you can check it out. The underlying mathematical model is isotonic regression. Okay, so spikes are out of the way. I consider extracting spikes basically separating the fluorescence traces. Since the problem of extracting online spikes is resolved, we'll just focus on these basically three portions. Okay, our scenario is very similar to what I proposed you before. We maybe analyzed 1,000 frames of our movie with the algorithm I presented before, Kaiman batch. We found some neurons, and we identified traces up to this point. Now I'm going to sit in this situation in which the online experiment, the real-time experiment starts, and we want to both fit each of these traces, so see how basically the activity of each of these neurons evolve, but I also want to identify new neurons that might appear in my field of view. Okay? So an example, the first step basically is performed by fitting. So there is a non-negatively square problem in which you basically fit each of these frames with these components. If you remember, there was an A matrix and a C matrix. That means that we solve an optimization problem in which A is known. The only thing we want to estimate is the vector of C for each neuron, for a frame. We fit this frame. And here is basically what's left out. So after we fit using the neurons that we are aware of, what is left in my field, in my frame, okay? And this is basically, this information then is nicely used to detect new neuron, because if something interesting appear in your field of view, okay, in your residual, something that looks like a neuron in your residual appears, it means that you, as you remember before, you didn't do a good job in fitting everything that was there, right? We looked at the residual. If the residual was perfect, this would be just white noise. If something meaningful appear, that means it's a new neuron, okay, that we need to account for. And the basic idea is this one. We just take 100, a mean of 100 of the residuals, and then whenever we pass a set of possible regions to a convolutional network, again, trained to recognize when one of these little square contains basically a neuron or not, okay? So the regions, this is called the region proposals. Basically, we propose possible regions by scanning a Gaussian and finding peaks in a Gaussian. And then all these basically proposed networks, proposed regions are passed to this network that decides whether we want to incorporate these neurons. And you will see incorporate neuron because it's added to the list of neurons that we already knew, or not, like happens in these cases. Okay? So summarizing again, we fit, given all the components that we already know, each frame, we look at the residual. If in the residual something that looks like a neuron appears, it means that we need to add it to the list of neurons that we keep on tracking. Okay? And to take this decision, we train the convolutional network. Okay. Other important part is how do we update the shapes. I'm not going to go into the mathematical details. The framework that we use is called online dictionary learning. But basically, you can see what happens in a real movie. So you can see this as, whenever this fire, this is updated, you see? Okay? So we update it, and we make it nicer and nicer and nicer. You can see even better here in a simulated data where a neuron appears here, and as more spikes are detected, the shape is refined. Okay? So what you want to do is to basically accumulate information. What's the trick that makes Kaiman efficient is that you don't have to keep in memory all the history of the frames. You just have some sufficient statistics, some coefficients that you store in memory, and will help you to refine these shapes. And also track their change in time eventually. So summarizing again what happens in an online framework, get the frame here, we motion correct. So first we initialize, of course, with 200, 400 frames. Then we use initialization to motion correct. This gives a very good template. We use the template. We motion correct. We estimate the spikes. Basically, we separate the activity of overlapping neurons and background. We separate them. Then there is detection of new neurons that are added, and also refinements of the shapes. And at the end, what we get as output is our activity at each time step that we can use then to close the loop in our experiment. This is an example on mesoscope data. So this is one of 6 planes that have been connected from a mesoscope. This is from Andrea Stolia's the data. This is the raw data. This is the inferred activity. Okay. Here, these little purple squares indicate when new neurons are found, and this is the noise, the reconstructed movie in real time. Okay. So this is going to start slow and then accelerate more and more. This is not a real time. Okay, so look at what happens. You see at the beginning, you see in the residual, you see that in the residual you have things that look like neurons. Sometimes are detected, sometimes not. So for instance, this guy stays there. That means it's not been identified as a neuron. But in general, the algorithm does a kind of a good job in cleaning up residual and making it look like it's white noise. And in the meanwhile, more and more neurons are found. Okay, so this data set is the data set that now we are going to analyze in our demonstration on Colab. Any questions? No? Everything is clear, or there is anything that didn't go through? Okay, good. Okay, what's beautiful about this is that now this is one processor that just need to keep in memory 100 frames. So let's say that we want to analyze the full brain of a zebrafish. Fine, we just take 40 processors, we duplicate, we run in parallel the analysis, and we can analyze the full brain of the zebrafish in 15 minutes. And this is the results of Kaiman of the full brain of a zebrafish. It was just 30 minutes of zebrafish that collected at 2 hertz. So, only 1,800 frames. At the same time, a few years ago, you needed a cluster of 10 computers to solve this problem. And now we can do it maybe potentially also on your laptop. OK, let's then look at the demo. You should now be pretty familiar with what we see. OK, so first we run the import. So we already installed this, as I told you before. The name was, I remember, demo on acid mesoscope. You set it to the GPU. You start the installation, and now basically we download the demo directly here. So again, you just have to tell him the name, and he will download it for you. We set up the parameter. Let's look at them again. Okay, frame rate, decay time. We are all familiar with this one. G-sig was the size of the neuron. Remember, half size of the neurons. P, the order of the autoregressive model. So basically, all of this is familiar. There are directly now some criteria of quality for these components. Why? Because now we cannot correct for them a posteriori. We want to do it in real time. So here you can add some of the criteria that you want to be fulfilled as the algorithm continue. So for instance, if you find too many neurons with small signal, you can say, no, look, I want larger transients, for instance, and you can increase this number. This is Arval threshold, the same as the other one. Downsample factor, if you want to downsample your data set, the number of background components, if you want to do motion correction or not, and if you want to do piecewise rigid motion correction or not. Everything is fine. So what we graciously call the sniper mode is the convolutional networks. You see all these things appearing. We called it the sniper mode. So if you want the convolutional network on, you say true. And this happens if you have classically looking neurons and not, more different things you expect the algorithm will not deal with. How many frames you want to initialize your algorithm from. So we run the batch algorithm on 200 frames. This is not the number of components you are looking for. This is an exaggeration. You have to set the maximum number of components that you expect to find. You might find more, okay? But the problem is that when you increase arrays, there is a delay. So what we do, we immediately create it big, okay? And then, if you really need it, we'll make it bigger. This is if you want to update in a distributed way. The shapes can be either updated at specific intervals, but they can take a long time, maybe 2 or 3 seconds, or you can randomly update them as you go by. So normally, if you are doing something in real time, you might want to do this, like randomly updating the shapes. How many regions you want to propose to the neural network. How many neurons you want to initially find, okay? So if I say k equal to a init batch 200, it means I'm going to run the batch algorithm on 200 frames, and I'm looking only for 2 neurons, okay? You don't need to find all of them. Actually, the algorithm will find most of them anyways. How many times you want to go through the data? This is important. If you're doing a real-time experiment, you cannot have epochs, right? It's just once as things happen. But if you are doing an analysis, you can just say, okay, I'm looping through the data a couple of times, just in case I missed neurons here and there. So we are looping through the neuron a couple of times. ShowMovie will not work here because we are on this notebook, okay? So these are basically the parameters that you need to play with. And there are not many, and I don't think they're very, very difficult to understand either. But if you have issues, please let me know. There's going to be an exercise afterwards, so be prepared. So we execute this part, okay, and now we run the online algorithm, okay? As we run the online algorithm, so of course, this is online, not for real, because everything is already on the hard drive, but this is a simulation of what would happen, okay? So this is first initializing, that's what it's doing, and at some point you'll see that the algorithm will start giving number of frames that are processed and number of neurons that are found. Okay, so we'll wait a little bit until this is done. Actually, the initialization is the one. Okay, it's initialized already. You see, it says epoch 1, 500 frames have been processed. In total, 37 new components added. Total of components is 39. Okay, so now it's processed 1,000. So you already processed 500 other frames. And so this movie is only 1,000 frames long. So now it's the second epoch. Okay, is going through the data another time. That's exactly what happens here. So what happens? Right now, this is basically prepared to be used in, to analyze your data on your hard drive. If you want to transform this into a real closed-loop experiment, that's what we are trying to do now. Because now you really have to optimize a lot of things, since from scan image to your computer, and then to have the GPU used efficiently. So there is some tricks there to be solved, but it's possible, and we are running at speed now. So you can have a look at the results here. Okay, not bad, right? In real time, just passing through the data a couple of times is able to find most neurons. No, there are some that are left out, 1, 2, 3, 4, maybe 5, 6. But when we actually compare with the human annotators, this is doing pretty well, around 75 to 85%, F1 score. You can, again, investigate what the components look like. You can make it much larger if you want. There are some parameters to increase the size of this, but I didn't want to occupy all the screen. But basically, it's the same representation that we had before. Okay? So you can see both the denoise data, and you can see, so this is one of the things that I think Simon's mentioned before, right? The algorithm here is failing a little bit, right? So yes, there are something that you need to tweak to make it work.
Typically, we found when it's giving something crazy,
yeah,
it's been exactly that. It's been the base
yeah.
line is somehow at the wrong spot.
Yeah. Yeah. Look, because no, I mean that's.
I mean, it's the this sort of moving average model, right? I guess.
It's not even a movie. It's all in the statistical model. Is counted the baseline, but
yeah.
if you don't estimate correctly this noise,
yeah.
that's the most difficult thing to do. How do you distinguish noise from signal? That would throw the algorithm away. The prior is Poisson.
Yeah.
So what happens? You expect a given frequency, and you have to give the right Poisson prior to make it work perfect, which you don't know.
Presumably, it wouldn't be too difficult to improve this to be able to deal
No,
with
I think it's possible. I think it's a lot of the best strategies to see what to go to your trace that don't look well and fix it. Yeah, and that's it. But it's possible to improve, definitely. Here it gives you a plot of the times. Okay, this is what the timing is doing. So for this, now is about 30 milliseconds. So we are working, of course, in optimized version of this algorithm that can go much, much faster. I have something now that works about 100 hertz. So we are getting there. You have to change the algorithm, and it's a bit of a work in progress, but yes, it's it. So this is the online analysis of data. Do you have any question about it? Was super clear? You're going to go home and use it? Okay, good. So since you understood, now you're going to do an exercise. You're initializing the algorithm with 300 frames and 20 neurons. Go on, play a little bit with it. How many of you are not familiar with Python at all? Is it understandable looking at the code, or is it total mess? At least the parameters should be understandable there.
It's very understandable.
Okay.
Are you pretty much only developing the Python version of
Yeah.
Python at the moment? So when did the MATLAB version kind of freeze? I mean, it's still there, right? But,
I don't know exactly. That's a question for Eftikios Pneumatikakis. We both are focusing heavily. Sometimes I see that he's also going there and fixing some issues in MATLAB.
But the MATLAB, it'll be only bug fixes at this point. Not
Well, there is in bug fixes. There is not online in MATLAB now, for instance, because we found that it was just faster using all these routines of Python.
Yeah, sure.
That's. I know. I mean, that's a problem. A lot of people know MATLAB and not Python.
Yeah,
so
postdoc is a MATLAB,
we prefer
only postdoc.
coding in Python, but people don't know it. So, but I think the things is shifting a little bit, but not.
Can you comment a little bit on the decision to go to Python from MATLAB?
So first, when I started, so I was more familiar with Python than MATLAB. But that said, what was very good for me was the infrastructure provided by OpenCV, the memory map capabilities of Python, the clustering, and the fact that it was open source. So the fact that if you didn't have money, you couldn't get the 10 toolboxes that were required, that was a problem for us. And sorry, if you put it on the cluster, you have to pay 1 license per node. That's, when you have 40 nodes, it's really not economically acceptable. So, yeah, these were the decisions. Okay, just to give you an idea what you were supposed to do, you were going to go back to your parameters and just change this one to 300, okay, and k to 20. And then that would have basically done the job. You would have initialized with a little more frames and more neurons. Cool. Let's move on. So I'm going to do this since there is plenty of time, Emily. There's plenty of time. So. OK, so again, you go to, now this is one photon imaging, endoscopic imaging. You want to open the demo pipeline miniscope with collaboratory. Again, copy it on your drive and get to, actually it's not necessary, so if you want, don't do it, I'll do it anyways. Save, start it. And start the installation, okay? If you want, actually, yeah, we'll go. I hope I will not be disconnected like last time. Cool. Let's talk a little about the theory behind it. So this is a Python implementation of a package that was already initially developed by Pengcheng Zhu. The paper is oh, sorry, I didn't put the reference to the paper. It's in a live paper, 2018. Pengcheng Zhu is the first author. That's the original algorithm. So then we worked together to port it, and it was developed in MATLAB. Then we worked together to port it to Python and to make it parallel with the infrastructure that we already had. OK, so let's look at one of these images again. Now, you can already appreciate, even knowing much about data analysis, how different are these type of signals with respect to calcium imaging signal. What is chiefly noted, how blurred are the signals, okay? How the background is, in some sense, taking over the majority of the signal. So let's talk about motion correction. This is something that Simon raised. So we were basically able to use exactly the same algorithm that we developed for Cayman by applying a high-pass filter to this image. So if you apply a high-pass filter to this image, what happens is that the borders will become sharper. And then when you're finding, basically, to match two templates, it's going to be much easier to match them. Okay? So there is this G-sig field. That is the size of the filter. In general, we use more or less the size of a neuron to filter. This is not used to change your movie, just for motion correcting. But if something fails in motion correcting, I suggest you play with this guy. Okay? Try, you make it larger, you make it smaller, and see if it works. This is the size of the filter, basically, high-pass filter. OK. So this is an example of, of course, we took the worst possible movie. But you might have raw data that looks like that, okay? And after some manipulation, you can get to these results. What happens? What is really the big thing that is changing here? Your point spread function becomes a disaster. So you are integrating a lot of signal across space. The main problem you have is that all this integration is polluting your signal. And it comes, even if you have a little neuron here, the signal might spread very far away from where the original neuron is. And on the top of it, if you have many neurons that are, if you're a densely labeled area, all these neurons will just overlap at some point and all their activity. And give rise to this type of background that is very difficult to capture with the previous model that we had. If you remember, we were trying to using, this product of two matrices to represent the background. This doesn't work here. So Pengcheng, here it is. Here is the reference. So Pengcheng thought about using an autoregressive model for the background, and it makes a big difference. Okay. So everything that I told you so far about the model is the same except the background. So the only parameters that are different from previously are the parameters that describe how do you interpret the background. Okay? Okay, so first what we do here is we don't try to infer how many neurons are in one area. Okay? We let the algorithm decide it. There are two parameters, where before we had only one parameter for a neuron, now we have two. So this one is what approximately you think the neuron is in real life, and here is that what it looked like in your movie. Okay? We use this empirical law of 4 times this number plus 1. So in general, what you start doing is manipulating this value and leaving this one at 4 g sig plus 1. If you want, you can have some predetermined binary mask, maybe that has been computed with some other software like PCA. And then you have emerging threshold that has exactly the same meaning as before. So the difference with respect to before is that, you remember, we had the patches, but we also were guessing how many neurons we had per patch. In this case, we don't have that anymore. And in terms of size, now we have two numbers. One, what do you think the neuron is in real life, and the other one is how it appears after the deformation due to integration of light in one photon imaging. Okay, so what's the idea? I'm going to give you a very rough idea about how this works. So Peng Cheng's idea was to basically represent the background, okay, as a linear combination of pixels surrounding an area. So let's say this is the center of your neuron, okay? You have a neuron that is more or less like this. So if you go sufficiently far away from the neuron and you take a weighted sum of the pixel here, this could be a good representation of your background in some sense. Because you're assuming what? You're assuming that the background is smooth and is going more or less everywhere and it doesn't change suddenly. So this is the meaning of this Rhind-Sykes factor that in general you probably don't want to change. You can keep it at this. When you set low rank background equal none, automatically the algorithm will switch to this type of background that is more computationally expensive but much more expressive. And you know, in general, you just want to set these two parameters, and eventually, if these become very computationally expensive, you can subsample your background. See, this is the number of times you reduce your background. Since the background is smooth, right, we can think about just reducing it and without losing too much information. We expect that the background doesn't contain high-frequency information in space. The first thing that you do is set these two parameters, in this case. Basically, in the Python version, not in the notebook version, you are able to move these thresholds back and forth and then find the ones that highlight best what you think are neurons. So imagine that you can slide these back and forth. Okay? In our, we were not able to get these in the notebook, so we just basically plot a histogram and let you more or less decide. We are working on that. We'll be able probably also at some point to be able to do it on Google Colab. And then again, you have the same idea of filtering components. Okay? Even though we don't set the number of components, we always try to exaggerate a little bit how many components we found. And at the end, we can use similar parameters to filter components. Okay? Filter out components that we think are not promising. And this is based, of course, on the signal-to-noise ratio and on the shape. Not on the convolutional network, because as you can expect, these neurons, they don't like at all what you find in the case of two-photon imaging. Is that concept clear? Like, you know, you look at the mask of the neurons, you can see nicely a nice donut with the black inside. When you look at these masks, they just look like spherical.
I mean, inherently, that information is going to be thrown away.
Yeah,
right?
absolutely. I mean, I don't know. Maybe there's somebody at some point will come up with an amazing algorithm, but at the time, right now, it's not the case. So let's go to our simulation. So we installed what we needed. We downloaded the demo, similarly to before. We start our cluster. This is all similar to before. We set the parameters that I described to you. This is both for motion corrections. These are for motion corrections. We motion correct. This works reasonably well for motion correction. So just this trick of adding a high-pass filter actually makes the job. You'll see it will not take long. It's already done. It gives you basically the shifts. In this case, it was already motion corrected. And it also gives you the image after this G-sig field. This is the high-pass filter version of the movie. So when you look at your, use your G-sig field and it doesn't, you don't see anything promising in this movie, that means that you have to, in this image, that means that you have to change it, most likely. We create, we load our memory map file, and now we start to set the parameters for the source separation part of the algorithm. I'm finding neurons. These, list all the parameters. And I mentioned to you before that you need to set these two parameters, the peak-to-noise ratio and the peak of the correlation image. So this is basically a correlation image that tells you how much, actually this is Spencer stuff. So this is actually something that's, yeah, that's your stuff actually. So this is how correlated are these pixels. And you can have you can visualize the histogram here, and to have an idea, we're using 0.8 and about 10. We need to add, if you can imagine, if once at some point we'll have a scroll here that will be able to threshold these values and see when this neuron will appear in the background. That will be the right threshold. Here we use 0.8 and 10 that are very plausible given the histogram that we see here. And then we run the algorithm. You will notice that this is slower. This is slower because this problem is inherently much more difficult. The number of parameters that you need to fit is much larger. So we'll have to wait a little bit for it to finish. And here, in the meanwhile, I'm going to explain what happens. Here you have your component evaluation sections. So here, for instance, we are requiring neurons with a very high signal-to-noise ratio, that they look pretty much like their average. We don't use the convolutional neural network. You realize, no, we cannot use it here. If you wanted, you could try your own convolutional networks and add it here. But it's going to be an added level of difficulty. It's going to take a little bit more. Yeah, this is not fast. Let me go 1 second here. I should have run it before. I'll explain what happens in the following. We don't need to run it. Same discussion as before. You will find neurons. Okay. If you took the union of these two guys, these are all the components that are found by the algorithm. Then you pass this algorithm basically through this filtering of components, and all these components are maintained while the other ones are discarded. You can also visualize, as before, the traces of the neurons that are accepted. Okay. See how much more diffuse is the shape in this case, right? It's difficult to get a very precise estimate of the location of the footprint. And also the ones that are rejected. In this case, you see they all like a little bit iffy, but probably some of them can be saved. But in principle, if we do things correctly, as was pointed out before, you might just need an interface that tells you, okay, keep these ones and reject these ones, and you are done. Okay. The reconstructed movie. Right, this is, the contrast is difficult to make it, but you see how nicely he was able to get rid of the background. Just see these neurons that turn on, and they are not really bothered too much by all this fluctuation that you see in the background of this movie. Okay. And I don't know how tired you are, but this is the last section of the talk. Okay, voltage imaging data analysis. That's recent work. That's what my lab has been working on, particularly Changjia, that is here today. Basically is the person that developed VolPy. You want to go again to Google Colab, open demo pipeline voltage imaging. Again, set your GPU and save. You're ready to go. Let's just run all of it. So you go run all, okay? And in the meanwhile, I will explain. I have too many sessions open. Cool. All right. So now this is installing VolPy, and we should get the results by the time I explained you more or less how it works. I'll try to come back so it doesn't kick me out. OK, cool. Now let's have a look at what this image looks like. This is one photon, okay, similar to the one photon that we saw. But how much smaller is the signal-to-noise ratio in this case? We basically cannot perceive any change in fluorescence looking at the movie. Whereas before, just naked eye, we were able to see that things were happening. If you remove the background with some nonlinear filtering, you start seeing things happening. You both see this subthreshold oscillation. You see neuron going up together, up and down together, and you see spikes appearing here and there. Now, this is Voltron. That is an indicator that actually is flipped. So when the neuron is active, it's actually less fluorescent. So we flip the movie here. And again, if we compare it with calcium imaging, we are order of magnitude far away in terms of signal-to-noise ratio. Also, whereas this, again, I repeat, was only sampled at 30 hertz, this was sampled at 400 hertz. That is really in the lower limit. Actually, we should go up a little bit. Okay? So why do we want to get all this trouble? Well, first, we have access to the membrane potential. So that basically opens the path to control different dynamics of the signal, check subthreshold oscillations, be very precise about the fact that a spike happened or not, things that calcium imaging doesn't allow. But there is also a plethora of challenges that come with these advanced type of imaging. Data sets. We are basically augmenting at least tenfold the amount of data that is collected. The signal-to-noise ratio becomes much smaller. Many of the mathematical assumptions that we're using, they are not valid anymore. We cannot anymore, for instance, represent the dynamic of the neuron with this auto-regressive process. You know, the fact that we have the non-negative matrix factorization framework, now it fails a little bit because the membrane can go up and can go down. So you basically want to be able to change all these models and adapt to something that is much larger in size. So the first thing that we did is, OK, let's collect as many data sets as possible out there. There are not many. There are not many. And most of them, they have 3, 4 neurons, OK, 5 neurons. So if you want to find a large number of neurons, you know, it's something exceptional. We just found this is the best we could find are data collected from the cortex in Voltron, and they have 50 to 60 neurons. We didn't see anything more than that. If you're aware of something, let us know. So the first thing that we did, okay, let's try to create a corpus of annotated data that we can use to train algorithms and evaluate them, but also that other researchers can adopt. They want to train their own algorithm. So what we adopted are these 3 images. We preprocessed a little bit data to obtain a mean image that looks like this. The correlation image, as I explained before, highlights active neurons, basically, and the correlation video. We extended from Spencer, and instead of compute, I don't know if anybody did it before. It's something trivial, but basically we take the correlation image on many windows. And they actually, highlight very nicely the activity of neurons, because it doesn't matter if you go positive or negative. This is a blood vessel, but basically this type of image, at least from a diagnostic perspective, is very nice to visualize neurons. So basically, we started labeling neurons by looking at these 3 images. Okay, and if the neuron was clear in any of these 3 images, we would select it. And so we basically, this is the amount of data that we have labeled. there are not many neurons, as you see. There are about 11 data sets here, 3 data sets here. What? 12? How many here? 12? 12 data sets here with 2 different indicators, but we would like to try other ones. If you have nice signals and you want to add to this list, we would be very happy to check your data sets. So the pipeline is still the same. The problem that we need to solve are the same again. I feel like bad going again through it, but I'll do it. So basically, you get the movie, you motion correct, you transform to a format that is easily parallelizable by your computer, then you do a segmentation. That's what I called before the initialization, a segmentation. Here, we want to find where the neurons are. Why? Because our computational problem of extracting the signal becomes much, much simpler if we already know which are the pixels that are interested. With calcium imaging, we could get away without knowing exactly which were the right pixels. Okay? But in the case of voltage imaging, it seems more difficult because of the low signal-to-noise ratio. After that, we want to clean up the signal, okay, and go from something that looks like this to something that looks like this. After that, we want to do some denoising and, we want to do some extraction of spikes. So basically, some type of thresholding that tells you when event happened. Okay, so motion correction. Motion correction, it works basically out of the box, okay, with a caveat that you might see during the demo. But it basically works well. You can use either rigid or non-rigid. You don't even need to high pass your data sets. It just works okay. Okay, so the first thing is that Changjia and I discussed, okay, let's see if we can find some type of supervised learning framework that might segment the neurons for us. So we went for something that's called mask RCNN. Mask RCNN, if you want to draw a very loose analogy with the visual system, has 2 pathways, the where and what pathway. So you have a basic feature extraction set of the network that has been trained on millions of other images, not even neurons, just other images. This is called the backbone. And then you have the head, in which you have 2 pathways. One of the pathways that basically assign probabilities of being an object. So basically the what pathway in the visual system. What is this? A neuron? Yes, 80% probability. And the second is the where pathway that basically provide you the segmented version of the neurons. So when you feed a couple of the summary images that we generated through this network, what you get is in the output is masks and associated a probability of being a neuron or not. And then you can play with that, of course. Yeah. Yeah.
Is the class box using is this happening serially? Is it getting the segmentation from the?
The segmentation is another network that does that. So it's UNet.
Class box assigning classes to individual pixels or groups of pixels or segments.
So there is a region proposal network, basically. But Changjia knows better than myself. Maybe he can give you even a better explanation. But
so class box both provide the class probability and also bounding box.
And I'm sorry, say it again.
A bounding box.
Oh, bounding box. Oh,
yeah.
Okay, so not
basically when 2 neurons overlap, if you have the bounding box, you will be able to see that it's 2 neurons.
Okay. Oh, I see. Got it. Thanks.
okay. So once this is an example of what it looks like when you apply to the different data sets. Of course, there are different data sets with different signal-to-noise ratios. This case is reasonably easy to deal with, and we have very good performance that we have quantified afterwards. But there are other cases, like in this case, for instance, or here where there is a big, a lot of overlap, where the neuron, where the network has a harder time to find the right contours for the neurons. Of course, this also depends on the fact that we had very few neurons to feed to train these networks. So that's why we say we really need a lot of neurons, because the more neurons we use to train, the better will be the network in identifying these contours. Once we found these contours, okay, what we basically do is parallelize per neuron. Okay, we take a neuron. Since we created our memory map file, we can just extract a context region around it, and then perform all the denoising operations around it. First thing that we do is we high-pass filter, because there's a lot of bleaching, photo bleaching, so we need a little bit to remove that, but there is also some subthreshold oscillations, and we want to get rid of them as much as possible in this phase in which we want to identify spikes. No. Secondly, we try to remove the effect of the background. As in the case of one-photon imaging, the background is going to be an important component that we want to get rid of. We don't use a model as complex as the one I explained for one photon, also because in this case there is kind of sparse expression. But what we do, we try to approximate the background with a lot of with SVD. So basically with the PCA with a given number of components. So we approximate the background with its components, and when we approximate it, we remove it from the original signal, and we try to clean it up this way. And then iteratively, what basically we do, we threshold and take a given number of spikes that we consider to be safe spike in some sense. So the highest spikes, we use them to build a template of what the shape of the spike might look like. We cross-correlate this template, okay, with sorry, I don't remember this one. Basically, we cross-correlate this with the original trace, okay, and this will give us much more precise spikes. You can imagine if you design a filter like this one and you match it to the shapes that you're trying to look for, what you will have much spikier signal, and that's exactly what you get. You go from here to here. At this point, you threshold again, okay, with an automatically detected threshold. And you use this denoise trace to repeat the previous operation, in which you optimize the spatial filter. This is equivalent to basically keeping fixed your signal and regressing on the spatial component. So you basically try to find the best combination of pixels that explain this, that can reproduce this trace. And then you go on this way. So again, it's remove the background, detect the best spikes, find a template, cross-correlate the templates to increase the spikiness. Now threshold, okay, get the spikes, and with this trace try to fit the spatial component. That will look at the end something like that. So similar to what you will get with one photon imaging. This is one photon imaging too. Calcium imaging. So this is an example of a data set that has been analyzed with VolPy, and is actually part of it is the data sets that now we are analyzing with our notebook that is hopefully running now. Okay.
Just a question on that.
Yeah.
Have you looked at cross-correlograms between these? And I wonder whether that is useful in, like if you're spike sorting, they can be useful in terms of seeing if you've got.
No, we didn't try. Good idea. Yeah. It is definitely. No, we didn't try. We just tried to. So in this first iteration, we are very stuck on this part. This one needs also to be improved, but this one is really, it's difficult. Okay. Now let's look at the noise. So we can do what we did before. We can try to reconstruct, in some sense, the original movie using the components that we extracted. So these are the spikes of the neurons, basically, that you see here. And now, before we had a time resolution of 30 milliseconds, and now we have a time resolution of 400 milliseconds. And of course, this opens the path to other type of questions that can be answered. This is a little bit of evaluation. Let's look at the demo before, okay? So again, you have frame rate 400 Hz in this case. You can pass some region of interest yourself if you want. You can manually label and then pass it to your objects. You can reuse weights that were computed in another movie. Let's say that you have different chunks of the movie and you want to reuse them. You can motion correct. G-sig field is the same that we use for the one photon, but it can work also without it. These are max shifts, strides, same thing that I explained to you, exactly the same. So these will perform motion correction equivalently to before, and you can see, I have a look here at the results of motion correction. Now something went. Is it looking like this for you? With two or only one?
With two.
Two as well?
Yeah.
Oh, something went well. It didn't go well here.
Yeah, I have one.
You have one, right? It should be one. I don't know why it's happening. Let me try again, maybe. So basically, you should see just one movie, and on the left, it should be before motion correction, and at the right, after motion correction. I'm going to let it run. No, sorry, that was just a visualization of the movie. Sorry, my bad. This is, I don't know why it's double, but basically this is what you want to see. Okay, so this side is motion corrected, this side is not. You see there is a little movement. It seems pretty fixed, right? Do you agree? I think it kind of seems successful. Now, if you look at the data after filtering, it still looks like there is movement. Now we don't know if this is real movement or maybe there is something underneath. Oh, sorry. Maybe there is some interesting biological process going on that looks like movement. To us, it also seems a little bit some waves of activities.
Can you low pass filter the motion correction? Because oh no, it's actually no, it's regional motion correction. Right, it's not rigid.
This is not rigid, but with rigid, it gets a little bit better, but
yeah.
The movement doesn't disappear. So two theories.
Real movement, right? I mean,
two theories. Either it's not real movement, or what happens is that since you are integrating across space, the movements is happening at another level. And at that point, it's very difficult to capture. Memory mapping, similar that you do. You transform in this format that is amenable to parallelize. Here is where you run your your network, which finds automatically the neurons and segment them. These parameters you probably don't want to touch for now. This shows the results of the segmentation. Okay, so you can check how it works with you. We wouldn't expect this to work out of the box for new data sets. So we need more data to train this network to generalize across different processes. Now, in this case, you see that is processing 13 spikes. It cannot parallelize, of course, in this case, but in general, it will if you use it on your computer. And now you can check here the results of different spikes. You can set here the number of spikes you want to look at. N equal 1, N equal 10, it's another neuron. And you can check the outputs, okay? So these are the identified spikes. This is the noise trace. This is the spatial component identifying in space. This is the spatial component highlighted, okay? Basically, that is it regarding this. A little bit of the results. When compared with threefold cross-validation on our data sets, or on this type of data, we did very well, above 0.85% F1 score. So basically, we're counting the number of matches versus the number of non-matches in some sense. And these are the matched neuron, and these are the disagreements, where the red is the ground truth and the yellow is what the algorithm found. The same for this other data set in which we do not so well here. But as you can see, it's not very easy to label even to be able to identify where neurons are here. And in this case, we only had 3 data sets. But you know, we were doing, I can, decent. These are the results. In terms of spike detection, these are basically simultaneous electrophysiology and imaging data. And both for the case of, you had 2 neurons from the zebrafish and 1 neuron from the mouse, we were doing very well. The average is 0.94 of 1 score. So we're really picking up most of the spikes. So I think this part works reasonably well. In terms of scalability, so yeah.
How big is the field of view in this? Because it looks like a lot of pixels per cell, way more pixels per cell than the previous table. Is that true?
Yeah, I mean, yes. So basically, this was what they used for the paper.
This was the Michael Lind data, was it? Or what
No, this is Voltron, Eric Schrader. So I don't know exactly what they did, but that's what they used in the paper to quantify, basically.
Unfortunately, this seems to be the standard in those papers.
Yeah.
The first proof of principle papers.
Yeah.
They'll zoom in on a cell and do
Yeah.
a patch of that cell.
No, that's a good point. I didn't think about it, but that's something definitely to take into account. The signal doesn't, you know, if you look at the, how do I go out? If you look at this stuff that has been extracted, I mean, it doesn't seem bad either. I don't know. In this case, I don't know, but we don't have a ground truth for this case. I don't think that once you denoise, I don't think finding the spike is really big issue. But you know, you need to nail down very nicely where is it the neuron.
With Voltron, but
yeah.
Voltron is one of the best at the moment.
Yeah.
So some other indicators may be less.
Absolutely. I know we have some images in which we cannot see nothing. No, literally, there is no signal. So I don't know where to put it there. Okay, but you know, all the data that we got, you know, we used for you know, and then other data arrived and we didn't analyze yet. But you know, the one that we got as a first, we analyzed all of it. Even this one, that actually, honestly, it's pretty tough to interpret. This is, you know, very tough to interpret, honestly. The scalability, so we are at the beginning, this is iteration 1, but you know, nevertheless, consider that these movies are like 400 hertz. Normally one small experiment is 36,000 frames approximately, so they go up very quickly. 50 neurons we can analyze using 35 gigabyte of peak memory when we parallelize on many processors. So the more processors you add, the more memory you use, but the more processor you use, the less the faster you will analyze. So basically, with our computer that is not that big, we can analyze this data set in about 9 minutes, I think it is. Is it 9 minutes? Yeah, approximately. And this is how the processing is allocated, and you know, see the most of the time is taken by the spike finding denoising algorithm. Okay, so let me is there any question before I conclude? Because that's it. You guys must be really tired. I get it. But is there any question? No? Cool. So what did I talk about here? Regarding calcium imaging, 1 photon, batch, and online. 1 photon, I talked about batch. There is also an online story, fresh off the press. It's 1 month ago. Gonna talk about this work next year. This is mostly work from Johannes and Eftichios. And for future directions, I plan to look into dendrites. There is currently an unsolved problem, so there is no algorithm that works with dendrites. Voltage imaging. So this is definitely the first analysis pipeline for voltage imaging. There is nothing out there. We presented together. We did a corpus of annotated data. So guys, knock yourself out if you want to try to train algorithms. For the future, we are very interested in doing this online. Now you can imagine that doing this online is really where the challenge is, because 400 hertz, that means that you really have to go at an impressive speed. And we have some good preliminary results there. Question? No? No. Yeah.
So, as I understand it, a lot of the problems with voltage imaging is that you get a loss of SNR over time, right?
Also, yeah.
Do you find that your algorithm has, or do you, first of all, in the data sets that you've got, did you have that? And if it did have that, does your algorithm work in those later frames?
That's a very good one. So we didn't quantify. At the beginning, we tried to use the results, so it can give you probably better results. But we try to use what we found, you know, since the first is the best. Let's try to use what we found in the first, right, to reduce, you know, the inference in the second one. I don't think we get a big difference. Do you have anything to add about that?
The change of signal.
Yeah, the fact that, you know, the first chunk versus the chunk 10. In chunk 10, you see no signal. In chunk 1, there is a lot of signal.
I think so. We divide the data into different chunks.
Yeah.
So even if the signal to noise ratio changes slowly, like in the same chunk, the signal to noise ratio generally keeps the same. So I think it won't.
No, just she wants to know is if we have a way to quantify when it's too late, basically, and it's already very difficult to pick up the spikes. You know, if you use 1 and 2, that's good. And then if you start using 7, the chunk number 7 left after 15 minutes, are you still good, or photo bleaching already destroyed your signal? We didn't quantify that. That's a good question.
But the signal to noise ratio indeed drops.
It drops, definitely. We know that it drops. That's no doubt. Then, so online, I think it's a great idea. Subthreshold oscillation, try to model, you know, what's happening there. It's not anymore a phenomenon that involves only one neuron. It might be, you know, multiple. How do you mathematically capture that type of signal? And third, subcompartment signal. So at some point, you can imagine you will be able to pick up the signal from a dendrites as it travels towards the soma. So it would be nice also to be able to extract this type of activity in the future. Thank you to the Simons Foundation, FTQs in particular. So we co-developed Cayman together for like the past 4 years. Lately, he's the one that is really taking care of it. We add some small improvements here and there, but he's really taking the load of it. Johannes also is working heavily on that, and Pat Gunn, both at the Simons Foundation. We'll also thank Liam, a lot of useful suggestions. People from the Princeton University for data, from Baylor College of Medicine, UCLA, and Cold Spring Harbor Laboratory. If you want to use Cayman and, you know, try yourself the hard way on your computer, you can find the repository here and the paper here. For VolPy, well, thank you to Changjia that, you know, single-handedly developed basically VolPy. Kaspar co-led this project, Podolsky from Janelia Research Campus. Thank you to Carlos Svoboda, Amrita Singh, Misha Arens, and Takashi Kawashima and Yu Shuai for the data we provided. Thank you, Adam Cohen and Michael Xie for the data, Johannes and FTQs from the Simons Foundation. You can find, again, at the same repository VolPy and the paper in bioRxiv. I would also thank my wonderful laboratory, really an exceptional group of very creative individuals. And above all, they are very fun. So I really like working with them. What are the things that we are doing in the lab? Now, real-time calcium imaging for real. So we really try to connect it to scan image. And it's actually going very well. We have some very good results. 3D behavioral analysis, we are trying to get some way to really capture in 3 dimensions the behavior of the animals. So really to map precisely in the 3-dimensional space the fine detail of movement, like single fingers. Imaging ferrets during Pavlovian conditioning, that is pretty tough. Corticocerebellar interaction in terms of computational problems is something very interesting. And together with Nico, we are looking at brain-machine interfaces using this technology, my technology, and the technology that he developed. These are my laboratory. These are the people in my laboratory. They are mixedly involved in many of these projects. And thank you for the attention and for the patience. And there is not even coffee. Amazing. I mean, that's surprising. You're still awake.
I've got one general question, which is, are you thinking much about how to deal with volumetric imaging data?
So there is something.
Other than just running on multiple slices, because
no, there is,
you can do that.
There is a version of Cayman that works with volumetric imaging data. There is also a motion correction algorithm that works with volumetric. We don't have bandwidth to develop it. But the idea is not different, because if you think about it, you know, what you do, you take your movie. If it's 2-dimensional, you make it pixel by time. If it's 3-dimensional, you do pixel by time. But now when you're looking at basically you're looking at your prototypical neurons, then what you're doing, you're basically doing, instead of 2-dimensional Gaussian in space, you do a 3-dimensional Gaussian. But then the rest is basically the same. It doesn't change.
So for calcium imaging, you were doing something to like quantify like 2 counts versus 1 count, right? In the height of the spike. Were you not?
Counts?
Yeah. Or like you were saying that the height of the spike mattered versus.
Yeah. The signal to noise. Yeah, the signal to noise.
No. But like, so if you have 2 events that happen close enough to each other, they just like contribute to 1 spike, right? And so you were trying to like discriminate like the height, like saying that like this is 2 events versus 1 event, right?
That's not exactly the way it works. The idea is that one. But you know what you're really trying to do, if you want to a little bit more details about it. Okay, so basically, you know, if there is a spike, okay, your kernel will look something like that. Okay? So what you're trying to find basically is to see, okay, if there are 2 events that are very close, what this will look like? It could look like this, but if you are slow, it could look like this. And if you have something like this, what happens? You will start to see modified the decay time too, right? So what you're trying to do, you're trying to fit all of these shape and find what's the optimal combination of these guys. Now I show you this, but it's not true because we don't have an integer number there. So what you get is something like this. These don't map really to spike. That's why I say it's not really spike. It gives you a little bit more information about the temporal event, but it doesn't tell you much. The height of these, you know, can be a little bit interpreted in relative terms, but in terms of spike, it's difficult. There is another, you know, paper from Eftichios. It's very nice. It use a Monte Carlo Bayesian approach to now try to get you integer numbers. So now the constraint is that, okay, you can only use 0, 1, or 2. Yeah. Find me the best parameters that fit my trace. And that works nice, but that's slower. Yeah, but that's nicer. Yeah, it works better. But basically, what we're trying to do is really to fit as well as we can this curve, knowing that the decay time is tau. Okay, so you estimate tau, a decay time, and now you say, okay, what's the best combination of these guys? But you add a small constraint. You say, I want to use as few as possible of them. Of course, otherwise it would be very easy, right, to fit everything. You just do this, right? Yeah. Instead, you say, no. I'll try to keep down and not to use them if I can. So that's the basic idea that is used in the algorithm to denoise. Good. If you have any question, feel free to send me an email, okay? I'll be happy to answer. Thank you again.